So now I'll go to this one, step potential. Step potential. Is that okay? So in that one, look at here, V of x is defined like this, okay? First let me draw, so then I'll define it, okay? V of x as a function of x, okay? It is defined like this. It is 0 here, it is V0 here, okay? So this is value V0, capital P0. Is that okay? So it is 0, this is the origin here. Again, it's going to continue here, okay? It's going to continue. So that means V of x is equal to, it's equal to 0 when x is less than 0. It's equal to V0 when x is greater than 0. There is no singularity in the potential. Potential is not touching infinity. Potential may be discontinuous. Singularity means when it is touching infinity, we say singularity, okay? Is that okay? So again, potential is discontinuous at x equal to 0, you can see here, but it is not touching infinity anywhere, okay? So potential is constant when x is greater than 0, potential is 0 when x is less than 0. This is the step potential. Can I say like this? Step, just like unit step function, isn't it? We say like that, isn't it? So now look at here. In this situation, we have two what you call situation. One is your energy of the particle, whatever you shoot here, okay? So that energy of the particle can be greater than V0. Energy of the particle can be less than V0, isn't it? You can have two situations. Now let me take case 1, situation 1, energy greater than V0, okay? I have energy of the particle which is greater than V0. Is that okay? Yeah. In this situation, we shall solve this Schrodinger equation in the side, left hand side, right hand side, and we shall proceed. Yeah.
Sir, potential V0, we are it's my own shoes, or we are choosing the potential height, or it is random?
I'm not getting.
I mean that potential height. Practically.
No, practically I don't think. Look at here. Practically no potential will go up to infinity, isn't it? Are you getting my point? You can have only for finite potential like that, isn't it? I mean, in the finite region. Quite bookkeeping, but we can use most part of it actually, okay? If suppose we have any potential which is very large here like this, isn't it? Suppose it is x equal to 0, this is V0, okay? Then in that case we can apply this kind of what you call ideas actually, okay? Yeah. Now obviously, yeah, again this you can vary in some physical situation. You can apply some what you call you can have some situation so that you can vary. Is that okay? Yeah. So I'll quote the book, okay? In many condensed matter physics book, again they will take this one, okay? If you take any device kind of condensed matter physics book, okay, so again they are going to apply this one, okay? Yeah. So now look at here, when I take the solution, okay? So in x less than 0, let me take x less than 0, okay? Let me try to solve the what you call Schrodinger equation. What is that one? It's a free particle solution, am I right? I think you should be able to write it quickly. Minus h bar square by 2m d square psi by dx square is equal to E into psi. E should be greater than V0. Again, E should be greater than 0, okay? Always here. What is the minimum value of the V? That is 0, okay? Yeah. So now look at here. If you rewrite this equation, what will happen is d square psi by dx square plus 2me by h bar square psi is equal to 0, okay? So d square psi by dx square plus, let me write it as k1 square psi is equal to 0, okay? The reason will come why I have taken k1, okay? Where k1 is equal to, so can you define? K1 is equal to, let me define it here itself because I need this one. K1 is equal to root of 2m e by h bar. Is that okay? So that your solution psi is equal to a e power I k1x plus b e power minus I k1x. Am I right? So can I directly write this solution? Solution when x is less than 0. Okay. Solution when x is less than 0. So can I write this thing directly, because we have already done these things. Okay. I'm going to write this one directly. Psi when x is less than 0 of x is equal to a e power I k1x plus b e power minus I k1x, okay, where k1 is equal to root of 2me divided by h bar. So similarly for x greater than 0, okay, for x greater than 0, so let me solve the Schrodinger equation. That will be h bar square by 2m minus h bar square by 2m d square psi by dx square plus v naught into, speak out, psi is equal to E into psi. Slightly different, isn't it? Now let me take that energy term this side. I am going to rewrite d square psi by dx square. So plus 2m E minus v naught, okay, divided by h bar square psi is equal to 0. Can I write like this? Quickly, speak out. And this one, again, this one is positive, okay, E minus v naught is positive. Why? E is greater than v naught, okay. So that's why I'm going to define it as d square psi by dx square plus k2 square psi is equal to 0. Look at here, why I defined it as k1, isn't it? So that was different. Now k2 is equal to root of 2m E minus v naught, okay, divided by h bar. Now the solution at x greater than 0, okay, let me just write it here. For x greater than 0, the solution psi of x and x greater than 0, that's equal to, can you just write a e power d square psi by dx square plus k2 square psi is equal to 0. What is the solution? A e power I k2x, b e power minus I k2x. K2 is real, okay? Yeah, a e power I k2x plus b e power minus I k2x. Check this out, where k2 is equal to root of 2m E minus v naught divided by h bar. Is that okay?
The coefficient should be changed again.
Coefficient a b, yeah, I have taken the same coefficient, am I right? I have to take some other coefficient c d, okay, c d, because we don't know, am I right? We need to find them by some other condition a b c d, but right now in the beginning we don't know what are those, isn't it? So that's the basic idea, okay. Now look at here. Again, if I take so again this has the energy E, am I right? The whole situation is, again, whether you take this solution or this solution, am I right? It has energy E, am I right? If you want to write psi x comma t, what you have to do? You have to take e power minus I e t by h bar term, am I right? Or e power minus I omega t term, isn't it? When you take term with e power I kx, okay, all of these are like e power I kx, what would happen? E power I kx minus omega t, isn't it? So when you see this one, okay, when you see this one, this is going to be e power I k1x minus omega t, okay. So another one is this one, e power minus I k1x plus omega t would come, am I right? Plus omega t or minus omega t? Minus is taken outside, one more minus, isn't it? Plus omega t, isn't it? So that's why this will represent wave traveling to the right, this will represent wave traveling to the left. We have discussed this one, isn't it? So that's why in this equation, so this one, this part of the equation will represent wave traveling to the right. You will get to know only after plugging in e power minus I omega t. Okay, just multiply the whole thing by e power minus I omega t, so that this will become time dependent wave function. Okay, in that situation you will get to know. Okay, so this will have x minus vt term, this will have x plus vt term, minus taken outside. Okay, So that's why this will represent wave traveling to the right towards positive x-axis. This will represent wave traveling to the left, that means negative x-axis. Okay. Now that's why I'm going to represent that one here. Okay. I'm going to represent that one here in the diagram itself. So A e power I k1x. Is that okay? Wave traveling to the right. Okay. That is represented by this part of the wave function. So similarly, wave traveling to the left, b e power minus I k1x. Is that okay? Where k1 is equal to root of 2me divided by h bar. Okay. Now let me again, before talking about this one, let me take a physical situation here. Physical situation is I am shooting the particle from this side. Is that okay? I am shooting the particle from this side. If I shoot the particle from this side means, look at here, again I am shooting the particle from x equal to minus infinity. Okay. So then again particle can come here, particle can go back here, incoming particle, so that is represented by this function. Okay. Outgoing part, again reflected particle, that's going to be represented by this function. Okay. Transmitted particle should be represented by one of these function. Am I right? Now again, if I take the situation that if I shoot the particle from this side, in this side, okay, in x greater than 0 side, there will be no particle which is moving in x again negative x direction, isn't it? Particle should again transmit here, isn't it, in this region. Again, this is the boundary, am I right? Something else is happening here. So particles should reflect here, or particles should go here into this region. In this region, so there will be no particle which is moving in this direction, am I right? In this region, because I have taken this physical situation that I have shooted particles from this region. If it is reflecting, it should have reflected from this one to this side. In this one, you will not have any particle which is moving in the negative x direction. Understand? Yeah. So now look at here. That's why what I do here is in this solution, I am going to eliminate this solution. Why? This will represent wave traveling to the negative x-axis, in the direction of negative x-axis when x greater than 0. Okay. So physically, in this physical situation, this is quite meaningless. There will be no particle which is moving in this direction in this region, because I have taken the situation of shooting the particle from this side. Okay. Yeah. So that's why I am going to choose d equal to 0. Is that okay? I am going to choose d equal to 0 so that my wave function here, that is, look at here, let me so that is like this, c e power I k2x. Okay, so can I write like this? In this region, so there will be only transmitted particles. Okay, this is reflected particle, this is transmitted particle wave function. Okay, so in this region there will be no particle which is moving in the negative x direction. So this, if you take e power minus I omega t, this will represent wave traveling along negative x-axis. That's why I am going to choose d equal to 0 according to this physical situation. So what is k2? Root of 2m e minus v naught whole divided by h bar. Speak out. So psi at x is less than 0, that's equal to a e power I k1x plus b e power I k1 minus I k1x. Okay, psi at x greater than 0, that's equal to ab c e power I k2x. Is that okay? You can write this h bar k1 and h bar k2 as p. Okay, p1 you can write as h bar k1, I mean momentum of the particle in this region. So p2 is equal to h bar k2. You can write as 2 pi by lambda 2 here. You can write as 2 pi by lambda 1 here. Okay, you can define de Broglie wavelength here. Okay, If energy greater than V naught, you can define de Broglie wavelength, isn't it? Using P. Or if you take this one, what is this one? If you multiply by h bar, what is this one? 2m E minus V naught. Okay. If you multiply by h bar, what is this one? This is nothing but P actually, isn't it? If you write E is equal to P square by 2m plus V naught, isn't it? If you solve it for P, it's going to be P actually. This is nothing but P by h bar actually, isn't it? So that's why you can define de Broglie wavelengths here, okay, in the region left hand side and right hand side, because it's a kind of what you call particle, freely moving particle, isn't it? Now look at here, we have those two statements, am I right, from Griffiths. What is that one? Psi should be always continuous. So second one, d psi by dx is continuous except at the point where potential touching infinity. Here we don't have any point where potential touching infinity. That's why d psi by dx should also be continuous. Okay? So that's why wave function and its first derivative should be continuous at x equal to 0. It should be continuous everywhere. It should be continuous at x equal to 0 also. Okay? Now I am going to apply continuity of the wave function at x equal to 0, continuity of the derivative of the wave function at x equal to 0. Is that okay? Now continuity of the wave function requires like, look at here, this is the wave function for x greater than 0, am I right? You can see here itself. This is the wave function for x less than 0. You have to substitute x equal to 0 here. You have to substitute x equal to 0 here. These two should match. These two should be equal at x equal to 0. Am I right? So look at here, psi x less than 0. If you put 0, that should be equal to psi x greater than 0, 0, isn't it? That gives a plus b is equal to c. I got one equation. A plus b is equal to c. Is that okay? Now again here itself, so take the derivative and write it down. D psi by dx, x greater than 0. Quickly. I k1 a e power I k1x minus, here also I k1 comes. I have taken that I k1 common. That's equal to speak out, minus b e power minus I k1s. Can I write like this quickly? I k1 will come outside when you take derivative, minus I k1 will come outside, I k1 I have taken outside. Negative sign.
The d psi by dx term x is less than 0.
Yeah, this is for x less than 0. Yeah, I'm just talking about this one. Less than 0, okay? Left hand side. So similarly, derivative of the wave function for x greater than 0. That's equal to, okay, I k2 c into e power I k2x, isn't it? Now that derivative should be also continuous, am I right? This is derivative in the left hand side, this is the derivative in the right hand side, okay? So when you put x equal to 0 here, when you put x equal to 0 here, these two should be equal. So that gives this one, am I right? I k1 a minus b is equal to I k2 into c, isn't it? Keep these equations. I'm going to keep this equation, okay? One side. Is that okay? A plus b is equal to c, okay? I can be cancelled. K1 a minus b is equal to k2 c, okay? So these are actually non-normalizable solution, okay? But still we can define probability current density. Is that okay? We can define probability current density here, okay? So now look at here. What is the probability of current density? What is the probability current density of incoming waves or incoming particle? So this part of the what you call solution, isn't it? That will represent incoming particle. Am I right? That's why probability current density of incoming particle. Can I say like this? Ji. Speak out. So that's equal to, what is this one? H bar K1 by M, I think mod of A square, mod A square. Am I right or not? Speak out. Is that okay? Yesterday we have done this problem, isn't it? I have written directly. So take this part of the solution, find probability current density corresponds to that one. Okay? Speak out. We have done yesterday A e power I K1x, isn't it? For this one, the corresponding probability current densities, I have defined it as Ji, okay? Probability current density of incoming particle. Particle is shooted from minus infinity, okay? So probability current density of reflected particle. This one. Yeah. Bisham, you kept your mic on. H bar K1 by M, okay? I think the same thing will come. Just check that out later. Mod B square with negative sign come. Anyone? Negative sign comes, I think. Check that out later. Is that okay? So what is J? H bar by 2IM psi star dou psi by dou x minus psi dou psi star by dou x, isn't it? Yeah, I think negative sign will come out, okay? So this itself says, look at here. So this is the, what do you call, this will represent particle going in the positive x-axis. This will represent particle going in the negative x-axis, isn't it? You got one more negative sign, okay? So similarly, J transmitted, probability current density of a particle which is going in the, so probability current density of the transmitted particle. So can I say like this? In the region x greater than 0, that's equal to H bar K2 by M. See the solution, okay? Mod C square. Quickly. Isn't it? Now look at here. Your reflection coefficient, okay? It is defined as J reflected by J incident. Your transmission coefficient. That is defined as J transmitted divided by J incident. Quickly find this one. What is reflected by incident? Mod reflected by incident. This H bar K1 by M got cancelled. Mod B square divided by mod A square. Or I can write as B by A mod square. This one equal to, be careful here, transmitted divided by incident, am I right? K2 by K1 will come. K2 by K1 C square by A square, mod C square by mod A square, or that's equal to K2 by K1 C by A mod square. Now this reflection coefficient will talk about what fraction of the particles are reflected. Transmission coefficient will talk about what fraction is transmitted or what percentage transmitted, okay? I mean, it is less than 1 actually. So if you make reflection coefficient plus transmission coefficient, it should give 1. Is that okay? Particles should be either reflected or transmitted, isn't it? Now you need to find this one. You got these two equations, okay? You need to find B by A, you need to find C by A. You have 3 unknown, 2 equations, but you can find the ratio. You can solve it for a ratio, isn't it? Can you quickly find B by A and C by A? B by A and C by A. A plus B, let me write it again. A plus B is equal to C. I need to cancel out C, am I right? K1 by K2, A minus B is equal to C. Let me subtract A plus B minus K1 by K2, A minus B is equal to 0, isn't it? If I take A common, 1 minus K1 by K2 plus B common, 1 plus K1 by K2 is equal to 0. I need B by A. Take it this side or take A this side. B by A is equal to, I'm doing it myself, do it yourself later, okay? B by A is equal to K1 by K2 minus 1 divided by K1 by K2 plus 1. Am I right or not? Somebody check this out. I've done roughly. Check that out. Am I right or not? This should be K1 minus K2 divided by K1 plus K2. Am I right? Simply. Now similarly, can you find C by A? Because I need C by A also. Do this algebra. Do this algebra yourself. B by A is equal to K1 minus K2 divided by K1 plus K2. So similarly, C by A is equal to, check this out, 2 K1 by K1 plus K2. Yeah, 2 K1 by K1 plus K2, isn't it? Now my reflection coefficient, that's equal to mod B by A the whole square. Am I right? Mod B by A the whole square, that's equal to, so K1 minus, again I don't have to take mod here, I can just take square because everything is real here, okay? So K1 minus K2 square divided by K1 plus K2 whole square, okay? So transmission coefficient, here you should be careful. What is this one? I think K2 by K1 will come. Am I right? K2 by K1 into mod C by A the whole square. Am I right? Check that out. So that's why. So that is 4 K1 square whole divided by K1 plus K2 the whole square. One of the K1 got cancelled. 4 K1 K2 divided by K1 plus K2 the whole square. You can check this out. If you add these two, you will get 1. Or if you find this one, okay, you can find this one by taking 1 minus of that one, isn't it? Transmission coefficient will be equal to 1 minus reflection coefficient. You can use that expression also. Check that out, okay? Because when you take square, I think you will get K1 square plus K2 square minus 2 K1 K2, isn't it? Now there are many gate questions on this one, okay? So now I hope you got all of this. All informations are there in the diagram, okay? While deriving, you better write all information in the diagram so that you can quickly, derive it, isn't it? Now, can you write them in terms of energy? Because in one gate exam, what they mentioned is, they mentioned the energy, this one in terms of electron volt, this energy in terms of electron volt. They were asking reflection and transmission coefficient, okay? Then try to write everything in terms of energy. So K1, what is K1? Root of, so root of 2me divided by h bar minus root of 2m e minus v naught by h bar the whole square, isn't it? Divided by root of 2m e by h bar plus root of 2m e minus v naught by h bar whole square. Am I right? So this is the reflection coefficient. What I can do here is, I can take root 2m outside, divide by h bar outside, cancel out. So can I write it simply? root E minus root of E minus V naught whole square divided by root E plus root of E minus V naught whole square. This is the reflection coefficient. Okay. What is transmission coefficient? Can you write similarly? 4 K1 K2. Root E, I think, let me write 4 times, okay? Root E minus V naught divided by root E plus root of E minus V naught the whole square. Just check this out later. How to remember this one? How to remember this expression? Okay. Now look at here. If suppose same potential exists in these two regions, then these K values would be same. Am I right? K1 will be equal to same potential. I'm saying same potential because here also E minus V naught come, here also E minus V naught come. Or put V naught equal to 0, then K1 is equal to K2. If K1 is equal to K2, then there will be no step potential. Am I right? If this V naught is 0, or if the same potential happens in this region, okay, then the K values are same actually, okay, in that region. So if you shoot the particle, there will be no possibility of reflection. Reflection coefficient should be 0. When K1 is equal to K2, look at here, your reflection coefficient is 0. I mean, among these two, if you have any confusion, you just put K1 equal to K2. If you put K1 equal to K2, this region is same as this region, isn't it? Or if you put V naught equal to 0, then K1 equal to K2. If you put V naught equal to 0, isn't it? So in that situation, particle should not reflect. Am I right? Your potential is 0 everywhere. It should not reflect. It should keep on going, isn't it? Then reflection coefficient is 0, 100% transmission. Is that okay? If you put K1 is equal to K2, you can see here, if you put K1 is equal to K2, this is 2 K1 K2 the whole square, it will give 1. That's how we can remember. If you have any confusion between these two, which one is reflection coefficient, which one is transmission coefficient, put K1 and K2. If you put K1 and K1 equal to K2, okay, reflection coefficient should be 0, transmission coefficient should be 1. Now I hope this formula makes more sense, isn't it? You may need this one in exam, okay? I'll tell you, in GATE exam, sometimes they'll ask some direct formula based question. I'll tell you, okay, during GATE exam to list out all formula, okay? So this whole thing, whatever we have done, this is an approximation method. Why? Because these are not normalizable functions actually, okay? This whole thing is an approximation method, okay? Now whatever we derive here, this can be seen actually, this can be seen in lab, okay? Not only in case of semiconductor devices, I think he might have given some application, just check that out, okay? In case of JET. But this formula gives a good, what do you call, experimental explanation for experimental aspect, okay? No need to worry, yeah.
To normalize wave functions,
You should go for wave packet solution. That's too lengthy. One thing is wave packet itself is lengthy. After forming wave packet, I don't think that whether, you need to find current density, isn't it? Using that wave packet solution, isn't it? Then you have to take reflection and transmission coefficient. That's too lengthy. So that's why we go for this simple method. Yes? No, I can't hear you. Yeah, this whole thing is a scattering field. Look at particle is escaping here as well as here. Look at here. Look at the wave function. Yes. This whole thing is this kind of potential will not allow what you call bound state at all, even though energy is less than V naught, isn't it? Let me take that the next situation. Let me take energy less than V naught, okay? Second case, energy less than V naught. you have energy E which is less than V naught, okay? In this case, particle may not escape in this region, but it can escape in this region. This also scattering state. This allows only scattering state, okay? There are problems in Griffiths, let me mention. Which one allow only scattering state? Which one allow only bound state? So before that, we need to touch all problem first, isn't it? Which one allow mixed state? That means for some energy, bound state, for some energy, scattering state, okay? So this means my potential is going like this, going on like this. Is that okay? That's the meaning. Is that okay? 0 here. In this case also it is scattering state. It may not escape in this region, but it will escape in this region, isn't it? Particles, okay? You will see this one. Now, can I write solution of the Schrodinger equation directly? X less than 0, x greater than 0? Yeah. That is what quantum, that yesterday I was trying to explain, am I right? I forgot here. That is the difference between what you call classical and quantum. Quantum mechanically, you have finite reflection coefficient, am I right? Classically, if energy is greater than V naught, 100% transmission should happen. So that is the speciality of quantum mechanics, okay? Are you getting my point? You got some reflection coefficient which is non-zero, am I right? So that is pure quantum mechanical effect. You can say like that. Is that okay? There is no classical explanation. There is no classical counterpart. Yeah.
So I'm not getting the scattering. How particles scatter?
Don't think scattering state is nothing but like whatever the scattering you have defined. Okay. I'm talking about scattering state means particle is not bound. It is escaping.
So here bouncer is there or not?
Yeah, you tell me.
Scattering state, it will scatter always.
No, scatter, we are talking about one dimensional problem. Don't think like your relay scattering or that kind of scattering. Are you getting my point? Those also comes in the same manner, but in a 3 dimension actually. We are talking about one dimension here, isn't it? Scattering state means particle is not bound. Particle is not going to stuck anywhere. It's going to escape again. It can escape here, isn't it? Even though you shoot from here, it can escape back, isn't it? That's what I'm saying. That's why I mentioned that what you call reading assignment. Read out that one, okay? In Jatili, first 4 part. Yeah. So now look at here. In this situation, what would happen? Let me write Schrodinger equation solution directly. You just work out later, okay? Incoming waves can be, again, I have taken one more physical situation again. I'm shooting the particle from this side. Is that okay? So incoming waves, they are defined as A e power I k1x. Outgoing wave, they are defined like B e power I k2x. Isn't it?
So K1.
Yeah, k1x only, sorry. Why? You are talking about the same region, am I right? Same medium, isn't it? Where k1 is equal to, as earlier, root of 2m E divided by h bar. So you know what is the solution here when E less than V naught? Isn't it? E less than V naught in this region minus h bar square by 2m d square psi by dx square, okay, plus V naught psi is equal to E into psi. Am I right? Just rewrite this one. H bar square by, sorry, d square psi by dx square, okay? Yeah, minus here, correct. Minus I k1x, okay? Yeah. D square psi by dx square. What is this one? Plus 2m E minus V naught by h bar square psi is equal to 0. Look at this equation. In this region, okay? I'm talking about x greater than 0. Where you are potentially equal to V naught here, okay, in this region. So now E minus V naught is negative because V naught is higher here. So that's why what we do here is d square psi by dx square minus 2m v naught minus e divided by h bar square psi equal to 0. We write like this. And we define this one as minus some kappa square psi is equal to 0. Is that okay? Speak out. Now the solution will become, what is kappa? Root of 2m v naught minus e, because v naught minus e is positive now, okay, by h bar. Kappa is real, okay. I take a negative sign outside so that this is a positive quantity. So solution is, look at here, psi is equal to a e power kappa x plus b e power minus kappa x. Isn't it? Carefully see this solution. This is for x greater than 0, am I right? Kappa is real, okay? When x tends to plus infinity, okay? When x tends to plus infinity, this part of the solution is going to infinity. This part of the solution is going 0. Speak out. See the equation. When x tends to plus infinity, this part of the solution going to infinity, this part of the solution is going 0, e power minus infinity 0, okay? Now, if you shoot the particle from here, okay, there is no possibility that particle can escape to plus infinity, am I right? This is classically forbidden region. Particle is not freely flowing here, isn't it? This kind of wave function have got j is equal to 0. There is no what you call current density at all. It's not freely flowing particle here in this region. Okay, earlier you had current density in this region also, remember. But now you don't have any current density here. Because of that part, again, particle cannot freely move to plus infinity. That's why particle cannot exist at plus infinity. Particle cannot go to plus infinity, or particle cannot escape to plus infinity. So that's why this part of the solution should not be there. That's why I'm going to choose a equal to 0. Is that okay? And in this region, the solution is, again I put the same coefficient, am I right? Put some other coefficient. Because AB is taken here, AB, CD, okay? And I'm going to choose C is equal to 0 so as to avoid this part. Why? This part will make the total wave function infinity at when x tends to plus infinity. I need to avoid this one. To avoid this one, I'm going to choose C equal to 0. That's why in this part, your solution is d e power minus kappa x. I'm not showing that this is a kind of traveling something, okay? I just write the solution here. This will not talk about any, I should not write like this, okay? Because these are kind of incoming particle, outgoing particle like that. This will not represent any current density, okay? Current density is 0 for this one. I'll just write this is the solution in this side. And this will go to 0 as x tends to infinity. Okay, that means particle cannot escape in this region, but particle can escape in this region. So that's why I can write here, one thing I can write here, J transmitted is equal to 0. Sorry. Yeah, J transmitted is equal to 0. Can I write like this? J transmitted, because you should take this wave function. Okay, e power kappa x, this is a real part of the wave function. This is a real wave function. Even though d is complex, it will give 0 current density. You know that one, am I right? J transmitted is equal to 0. If J transmitted is equal to 0, transmission coefficient is equal to 0, am I right? Is that it? If this is 0, then the reflection coefficient should be 1. I don't have to solve that all actually. Yeah.
सर यहाँ ग्राफ को कैसे दिखाएंगे सर?
Yeah, we shall do. Questions are there, am I right, on graphs. Kappa. That's why I defined this one as K, So where using this K you can define de Broglie wavelength, so 2 pi by lambda. So here you can't define any de Broglie wavelength, okay? This is classically forbidden region, okay? Using this kappa you don't define any de Broglie wavelength, okay? Because it's not freely moving particle at all.
How can we write this expression V naught minus C? Because kinetic energy.
What kinetic energy? No, that is again to solve Schrodinger equation I have written like that.
Okay.
Isn't it? Quantum mechanically, Schrodinger equation gave solution what we shall do, isn't it? Some non-zero solution. Particle can be there also, isn't it? That's what Schrodinger equation says. But remember, it's an exponentially decaying solution. In classically forbidden region, exponentially decaying solution. You can remember like that. Forbidden region, exponentially decaying solution. Okay? Now let me ask one question. If I take step potential like this is positive x-axis, V of x, this is V naught, okay? And I am shooting the particle from plus infinity, okay? What is the solution here? Incoming particle, you can write some a e power I k1x, am I right? You can write outgoing particle. Suppose energy less than V naught, okay? E less than V naught. Or let me first take E greater than V naught. If E greater than V naught, you can have reflecting particle, am I right? B e power, look at here, mistake. Why? So now incoming particle means it should be negative because it is moving along negative x direction, okay? It is positive I k1x. Can I write like this? K1 is equal to root of 2m e by h bar. Look at here, how the equation changes when you go to positive x and when you change positive and negative x axis, isn't it? Yeah, this is now incoming wave. Incoming means incoming towards this what you call step. Is that okay? Now this is the what you call particle moving in the negative x direction. That's why negative sign should be there, isn't it? So this is particle moving in the positive x direction, plus should be there. Okay. Now if suppose energy is greater than V naught, here also it's a traveling wave, isn't it? If energy greater than V naught, then it will be represented by e power I k2 minus x, where k2 is equal to root of 2m e minus V naught divided by h bar. Look at how equation changes, okay? Reflection coefficient, transmission coefficient, those remain same. Those depends on V naught and E actually, okay?
For E greater than V naught.
Yeah, this is for E greater than V naught. Okay? For E less than V naught. For E less than V naught, this part remains same, am I right? This part of the solution remains same. But here you should define a kappa. What is kappa? Root of 2m V naught minus E by h bar. Isn't it? Now how do you write the solution here? Tell me. Again, here if you solve Schrodinger equation, you will get AB C e power kappa x plus D e power minus kappa x. Which one you remove, which one you keep? Quickly tell me. Isn't it? Energy less than V naught. This is the solution where kappa defined like this. Now, which one you keep, which one you remove? Speak out. Why?
Because x equal to minus infinity.
Yeah, if you shoot the particle from here, it cannot escape to minus infinity. This is classically forbidden region, am I right? In that situation. So then, as x tends to minus infinity, your wave function should go 0. You should not have any probability of finding the particle in that region. Okay, both of them will give current density 0. But in the physically, in the physical situation, particle cannot escape to minus infinity. So as x tends to minus infinity, this will blow up. Minus of minus plus, okay? That's why you should choose D equal to 0. You should D equal to 0, you should keep this one. That's why the solution here is C e power kappa x. Don't forget. Is that okay? Here e power minus kappa x, it should be like this kind of exponentially decaying solution. Here e power plus kappa x, it should be like this. Can you grab the logic now? The wave function should be exponentially decaying type in the classically forbidden region. But be careful when you are dealing with negative x-axis, okay? Don't write e power minus kappa x in the negative x-axis also. Now, there are very frequent questions. Yeah, let it be. Yeah, speak out. Yeah.
Even though we are seeing that transmission coefficient is 0, there is a exponential wave function in that.
Yeah, you have finite probability of finding the particle, okay?
So how these two things are related? We are getting transmission coefficient is 0, but
No, transmission coefficient means particle should escape in that region, okay? Transmission coefficient means particle should keep on, again here J transmitted 0, am I right? This is incident reflected, J transmitted 0, that means particle should be able to move freely in this region actually. That's not happening here, okay? That's why we write transmission coefficient 0. Where do you collect the particle? Here you can collect reflected particle, am I right? Somewhere at minus infinity. But here you can't collect the particle, isn't it? But you have some finite probability of finding the particle. Classically, this would not happen, am I right? There is no possibility of finding the particle in this region. Okay? That is the difference. Kappa, this is same, isn't it? Just try to solve Schrodinger equation in that region, you will understand. Okay? Try to do whole this derivation and submit, okay? You will, once you do this one, you will remember all of these facts actually, okay? Once you do the derivation and you can answer any MCQ. Yeah.
If particle exists in that kappa region, then why it cannot have the de Broglie wavelength?
No. Here, look at here. De Broglie wavelength you can define only for what you call when kinetic energy is positive, am I right? You can define momentum of a particle. Momentum of the particle you can define only when kinetic energy is what you call positive, isn't it? This is the region classically which is kinetic energy is negative, okay? You can't, de Broglie wavelength is what you call, the idea will be, look at e power I kx, this can be written as cos kx. Now cos kx, if k is equal to 2 pi by lambda, this has a wavelength lambda actually. This if you think of a wave, this has a wavelength lambda. Or if you think of this wave, e power I kx minus omega t, am I right? This has a wavelength 2 pi by k. You can write it as h by p also. Just check this out. Just multiply by h bar or h, okay? Is that okay? So, but in this region, you don't have traveling wave. This is a traveling wave, am I right? These are traveling wave, isn't it? These are traveling wave function, but this is not traveling wave function, isn't it? Only for traveling wave function you can define some wavelength, isn't it?
Then what's the wave function?
That I have drawn here. You can't define wavelength for that one. That's what I'm saying. There's an exponentially decaying solution there. You can't define wavelength. But here it's a sinusoidal. You can define a wavelength. Or if you take time term, it's a traveling wave, isn't it? That wave function represents traveling wave. There you can define wavelength. And that is de Broglie wavelength. We say like that. Is that okay? Speak out. That's why you can't define de Broglie wavelength in this region, okay? Classically forbidden region, okay? Now, again, usually they may ask this kind of question, okay? What is the wave function plot, okay? let me take energy less than 0 first, okay? E less than V naught, okay? In this situation, so plot the wave function in this region and in this region, okay? That is the question that they may ask, okay? V of x. Now look at here, your solution is a e power I k1x plus b e power minus I k1x. Am I right? That's the solution. So now again, they usually ask mod psi square of the solution, okay? They usually ask mod psi square of the solution in this region, okay? Now this can be written in terms of sine and cosine, isn't it? This can be written in terms of sine and cosine. So here your solution is e power minus kappa x, am I right? A, B, C. Let me take C here, okay? In this region. So this can be written in sine and cosine. That's why here your mod psi square should also be sinusoidal actually. And it should be positive. You should not take negative, okay? Mod psi square cannot be negative, isn't it? You better to draw it like this. Is that okay? And next one, in this region it is exponentially decaying, am I right? Suppose if you start here, it should exponentially decay your solution. And curve should be smooth. Curve should be smooth. Why? There is no derivative discontinuity. If curve has a sharp edge, derivative discontinuity, yeah, curve should be smooth here.
That can happen when potential is infinite.
Yeah, here potential is not touching infinity. That's why derivative should also be continuous. Okay, that's what we have taken in case of reflection and transmission coefficient. Okay, so this is the curve, and in the again wave function should be continuous, derivative should be also continuous. That means there should be not breakage in the curve. There should be no sharp edges in the curve. Remember. Again, you need to solve some MCQ, then you will understand, okay? Unless you apply whatever you know, you can't test it, isn't it? V naught. Now let me take energy greater than V naught. Be careful in this situation. Be careful. Here it is a e power I k1x plus b e power minus I k1x. Am I right? This can be written in terms of cosine and sine. Am I right? Some a dash cos k1x plus b dash sine k1x. Am I right? But here again, if you shoot the particle from here, the solution is ab some c e power I k2x. Am I right? Speak out. That's why be careful while writing the mod psi square here. We don't write psi here. We usually go for mod psi square. Okay? As a function of x. Here it is sinusoidal. If you take mod square also, it is a sine square or cos square, isn't it? That's why your solution will be like this. Okay? Now what is in this region? What is mod square of this one? What is mod square of that one? Constant, isn't it? E power I theta, mod square constant. So that it should be like this. Smoothness should be there, okay, in the curve. Why? Derivative should be continuous. Is that okay? They may ask you to plot mod square. Okay, so in the option they may give the breakage in the curve, that means discontinuity. That cannot happen. Wave function should be always continuous. Okay, they may give some sharp edges, okay, like this. This kind of sharp edges. That cannot also happen. Or they may give this part of the function in the negative axis. Mod psi square, it cannot be negative. Like that they manipulate options, okay? No, it can touch x-axis, but it cannot go beyond x-axis because mod square is always positive, am I right?
Can it be in the upper side?
Yeah, it can be in the upper side also. Can you plot?
Sitting on
So can you plot square of this function? So try to plot square of this whole function, okay, using GeoGebra. Square.
Because I had seen in one of them that one was maybe beta percent.
Yeah, it may be in the upper side, but it cannot be. It cannot go down. That's what I'm saying. I think they don't give confusion in that. Okay. So try to plot square of this one. Square of this one. I think then you will understand completely. Okay. That's a good question. Because what will happen is when this both exist, when cosine is 0, sine will be non-zero, isn't it? When you square this one. When cosine is 0, then sine will be non-zero, isn't it? Cos 0 is non-zero. Sine 0 is 0, isn't it? That's why it may shift upward. Okay? Square of that one. That's what he's saying. Okay? Just try to plot this one, square of this one, then you will understand. Okay? That's a good question. Next one is, I think, if suppose I just so change this axis, okay? So then I hope you should be able to plot this one, isn't it? If suppose V0 is here, it is 0 here. In that case, don't plot like this. It will be like this, isn't it? If suppose energy less than V0. In this region, it is exponentially decaying. In this region, oscillatory. Oscillatory, we say oscillatory. Okay? Yeah, I think it will shift upward. Okay? Just try that out. Because cos, when cos is 0, sine will not be 0. When both of them will be 0, both of them will not be 0. Am I right? Sine theta plus cos theta. Isn't it? Both of them. For none of the theta, both of them will be 0, isn't it? That's why it will shift upward. That's correct, okay? It will shift upward slightly, okay? It will not touch x-axis, okay? That's correct idea. So try to grab as much information as possible from each and every problem, okay? Those information will be helpful in solving the question, okay? I think now today you can solve all MCQ, rest of all MCQ, whatever remained on this second chapter of Griffiths, okay?